Well, this is going to be a whole lot less pretty, unfortunately. Let's see if this works, though. Okay, so yeah, the next chapter is on conjugated dienes. I guess a nice example of this is 1,3-butadiene. And basically a conjugated system will have two double bonds that are separated by a single bond. So if we draw the p orbitals of a system like this for the various double bonds, you will see that you've got a series of, in this case, 4 p orbitals. So this is different than an isolated double bond system, say something like this. And if we were to draw the p orbitals of this, we would have, here's one double bond, here's the other. But in this carbon here, we've got 2 protons sort of, and it's blocking the arrangement of all these orbitals being in a row. So this 1,3-butadiene is conjugated. This diene here, which is 1,4 pentadiene, this would be basically a non-conjugated system. Non-conjugated. I guess there's another one we could talk about, which is this. So when you've got 2 double bonds and they aren't separated by anything, in a system like this, the double bonds aren't actually one set of double bond, they're actually perpendicular to each other. So in one sense, it'd be one double bond is on the x-axis, the other double bond is on the y-axis. So they're not in the same space. So this type of double bond system, the actual name for this functional group where you've got the center carbon here would be sp. These are called allenes. And the system here would be accumulated system. But what this chapter is all about is these conjugated systems here, like 1,3-butadiene. They've got a increased stability which comes with conjugation. So that's the interesting thing. Now, I guess normally I would scroll, but I can't do that. So I am going to clear this. Okay, next bit. So how would we make these? We would have seen this before. The simple way to do this is NBS, UV light. This is an allylic bromination. We did that before. It's a radical reaction. And then we would do what we did in organic 1, which would be an elimination with, say, tert butoxide, potassium tert butoxide, tert butanol. And this will give our diene. Now, when it comes to these, with the beautiful sort of all of these orbitals lined up. Most textbooks take the time to discuss molecular orbital theory at this stage. Molecular. So when we first talked about molecular orbital theory, we would have bonding orbitals and anti-bonding orbitals. And so if we had like a 1s orbital coming together with a 1s orbital to form bonding, the bonding orbital would be lower in energy, and that would have the two orbitals that would, so this would be a sigma bond, which would be in phase, and then the anti-bonding orbital would be up here, and there would be no electron density because there'd be a node right here, node, and they would be out of, the two orbitals would be out of phase. So this would be the sigma star. Now, when we, and so this would be the 1s, put a little electron here, put a little electron here, and then overall, you put them both in the bonding orbital and you formed your sigma bond, which is made up from the two s orbitals. So when we did this in Organic 1 or even in Gen Chem 1, there's basically a rule about conservation of orbitals. So you start with one orbital here, number 1, here's number 2. And when we make our molecular orbitals, which are in the middle, here's number 1, here's number 2. So we start with 2 atomic orbitals, and we make 2 molecular orbitals. So in a system over here where we've got 4 p orbitals, if they're all coming together to make a molecular orbital, we should have 4 different molecular orbitals for a system like butadiene. So I'm just going to draw them all out. Oh, darn it. Wait a second. I'm just going to draw them all out here. So I should be able to make 4 molecular orbitals, and I'm going to just put them one on top of each other based upon their energy. And so this is the lowest one, which is given a number psi1, psi2, psi3, psi4. So the lowest one, all of the orbitals, the phases align perfectly. So this is the lowest energy one. Then as you go up, each time you add a nodal plane. So I'll draw the little nodal plane in blue. So the nodal plane is going to be right there. So when you cross from one side of the nodal plane to the other, the phase has to change. So the second highest orbital would have these 2 in phase and these 2 in phase. Then when you go up another level, so instead of just one nodal plane, there'll be 2, 1, 2. And then we're going to draw the little phases here. So every time you cross a nodal plane, you have to reverse the phase. And then in the last one, there's 3 nodal planes. 1, 2, 3. And here we go. So they completely alternate. Now, in each one of these p orbitals, we've got 1 electron. So 4 times 1 is 4. So we've got a grand total of 4 electrons in our molecular orbitals. So these 2 at the bottom are our bonding, and the 2 at the top are our anti-bonding. Now, the other thing which is really interesting here is that all the chemistry takes place, because remember our little rule, negative goes to positive, this type of thing. When we're moving electrons around, electrons are moving from, they're always at, the electrons that are moving around are always the ones at the top of the energy scale, right? So in a system like this, there's basically been some names given to enter the highest occupied molecular orbital and the lowest unoccupied molecular orbital. So they've got little names like, so this one here is the highest occupied molecular orbital. So the HOMO. And this one here is the lowest unoccupied molecular orbital, sometimes called the LUMO. So there's a class of reactions we did last class, actually, with the Claisen condensation. The pericyclic reactions, where a lot of the way that electrons are moving around is it's an interaction between the HOMO and the LUMO. And so we're going to see this a bit later on in this class. But anyway, so yeah, the interesting thing is that you can sort of see in the lowest energy molecular orbital here, all of these things overlap. So it's like all of the electrons can zip up and down between all four orbitals. Here, they're zipping across between those two areas. So it's two isolated double bonds. And then when you get into the unoccupied molecular orbitals, if electrons ever got there, then in this case there's overlap here, and in the last case there's none. There's nodal planes everywhere. So it's just we'll see how this works a bit later on. I think that's all I wanted to say. I'm going to do is I'll save this. Okay, and then I will clear it up. Now, so there's two reactions that I want to talk about, at least for conjugated systems. The first is something we've seen before. So so we did, at the very start of this class, we did take an alkene, react it with HX. Okay, I'm glad that people can hear me. There must be something wrong with your speaker. Anyway, this is all being recorded, so if you miss something now, you should be able to hear it a bit later on. Okay. Okay, so we did this at the start of the term, right? This little part here, A or B. So if we take an alkene and react it with HX, do we form A or B in this example here? You're right, it is B, because why do we form B? Because do we want a carbocation like this, or do we want a carbocation like this? So this is basically Markovnikov's rule. We form the most stable carbocation. So that would arise from this intermediate. So that forms B. Okay, so with the addition of HX, so this was the rich get richer, right? Okay, let's see here. I will erase some of this stuff. So we did that before, rich get richer. Now, if we look at an addition of HX to a conjugated system, there is an added twist to this. So the first step, we will have the rich get richer. So we're going to, if protons equal money, the carbon with the most protons gets the money. So our intermediate would look like this. And so naturally, X could come in and attack, and this would give us but we also form another product here, and that is this one. Any idea how the product over on the left-hand side forms? Right, it's resonance. There's a resonance structure here, and let's draw this in green. So if we move these arrows here, there is a resonance product that looks like this. And then our X minus would come in and attack, and that would give us this product here. So with conjugated systems, the intermediate that you are always going to form is the resonance stabilized carbocation. So whenever we're doing an addition of HX to a conjugated system, we want a resonance stabilized. And there's two different products that can form from this. So the product on the left and the product on the right. And they've each got different names. So if we basically number our first 1, 2, 3, 4, you'll notice here that the two things are added on carbons 1 and 2. So that on carbon 1, we get the H, on carbon 2, we get the X. Over here, 1, 2, 3, 4. On carbon 1, we get the proton, and on carbon 4, we get the X. So this is called the 1,2 addition product. And this is called the 1,4 addition product. Now, one of these tends to form faster, and one of these tends to be more stable. Any idea which one is which? And when it comes to which one is more stable, think about stability with regard to alkenes. Right, the 1,4, okay, so remember for alkene stability, Mono is less than di, which is less than tri, which is less than tetra. And this was because remember, the more alkyl groups, the more hyperconjugation, so that stabilized it. And then another reason it has to do with the bond strengths. sp2 bonds are stronger than sp3 bonds, and there's more sp2 bonds in a tetrasubstituted thing bonded to carbon. So this tends to be the more stable. This is thermodynamically more stable. And the 1,2 product tends to form faster. And this is often associated with the fact that there's a proximity effect between when this initial double bond attacks the proton, that H minus, the X minus is close to the positive charge, so it can come back and attack more fast. So there's a question about alkene stability versus carbocation stability. In both of these cases, we form the most stable carbocation, right? We don't think, so we've got a resonance stabilized carbocation. It's, remember, it isn't a combination, these aren't discrete molecules. They're the same molecule, but we can't draw them as one molecule. So we just draw them as two, but really this positive charge exists on both places. So it's resonance stabilized. So a nucleophile can attack either place to form two different products. So in each case, they come from the most stable carbocation, which is the resonance stabilized carbocation. Now, why is this important that one forms faster and one tends to be more stable? So what happens here, and I'll save this. What happens here is, I'm going to erase everything too. Clear. Is that if you do this reaction at different temperatures, you get different products. So if you do this HBr at 0 degrees, oops. No. And if you do this at 40 degrees, let me look at the data here. I've got some data. Data is good. In the first case, at 0 degrees, you get 71% of the 1,2. This is the 1,2. This is the 1,4. And 29% of the 1,4. At 40 degrees, you get 15% of the 1,2 and 85% of the 1,4. So yeah, the reason why this is important is that you can manipulate the ratio of products based upon the temperature of the reaction. So when you set out the reaction to form the product that forms the fastest or the least stable product, I should write something else here. So the most stable one, this is what we call the thermodynamic product. And the 1,2 product, which forms the quickest, we call this the kinetic product. So one reaction will be under kinetic control. So this one would be under kinetic control. And the second reaction at the higher temperature This one will be under thermodynamic control. Because you get the most stable product is your major product. So, and you can manipulate this by the temperature. So the best way to sort all of this out is I'll draw a little energy diagram. We're going to go back to our friend, the energy diagram. And so remember, the first step in this reaction is exactly the same. We form the most stable carbocation, which is the resonance stabilized carbocation. So let me save this little diagram here. And let me clear. So here's an energy diagram. Reaction coordinate. No, oops, this is energy. Reset. Free energy. And this is the reaction coordinate. Okay, so starting material, come up, and here's our carbocation. And this is the resonance stabilized carbocation. Actually, I'm going to draw this. This one should be higher. Now, from this point, there's two departures that we've got. So the kinetic product would be something like this. So this energy diagram, this little hump here, this delta G dagger, and I'll put kinetic here, is going to be a low energy energy barrier. And for the thermodynamic product, it's going to be slightly higher, but the product is going to be lower, right? So this would be delta G dagger thermo. So in this one in green should be lower than the one in red. So hopefully I've drawn that to scale. So this is basically how this works. So when reactions are under kinetic control, when it's under kinetic, you will form this would be the 1, 2, green. So the delta G dagger kinetic is less than delta G dagger thermo. So you've only got enough energy to go over that blue energy diagram, that blue energy barrier, and it is irreversible. So if I label like this is A, and this is B, and this is C, you're in a situation here where A forms B, and really not much goes to C. So we've got, this is low temp, right? Low temperature. Now, when the reaction is under thermodynamic control, you heat it up. And so this makes the, under thermo, this makes this process from A to B in equilibrium. So some of your reactants might go over to form B here, but there's enough energy in the system that it can do the reverse reaction to go back to A. And then A will start to form a bunch of C. And because it's the product C, the energy is way down here, there isn't enough energy to go backwards over that larger to do the reverse reaction. So in thermodynamic conditions, the key point is that the delta G naught of the thermo is lower than the delta G naught of the kinetic. Remember, so this is this energy. So one is irreversible because you don't provide enough energy to the system, and the other one is in equilibrium. And so you form the more stable thermodynamic product. And that's why the ratio is 85 to 15. There's a natural equilibrium where you're still going to have some B in the system. Likewise, when the reaction is cooled, the odd molecule will have enough energy to overcome that larger delta G thermo and form some of C. So this is basically, there's two different types of products: kinetic products, thermodynamic products. So yeah, the conjugated diene system basically in organic chemistry classes there's two take-home messages they want to tell you about. Number one, giving you sort of a refresher on molecular orbitals and drawing them, which I briefly did. And the second being on reactions that are under thermodynamic control or kinetic control. And it's basically, typically it's the temperature which the reaction's carried on at. And so if we've got, let me save this. Let me clear it all. So if we've got a example here, let's do this. HCl, for example, HCl. How many different products could we? This one's slightly different because it's not symmetrical. Does that matter? We will soon find out. Okay, so let's do an analysis here. So the rich get richer. I'm going to start on this end of the molecule. So there is one little nuance here, is that there's two ends. And so our intermediate would look like this. And then this is in resonance with this. And then our chlorines can attack either one, and we would have this. So this is the 1, 4, 1, 2. Now let's just do the other side too. So let's put HCl over here. Let's do this one in red. So this attacks here, that goes there. Form one product. And this is in resonance. And this would give these two. So there's actually two different 1,4 products and two different 1,2 products. So typically when I ask these questions on exams, I use symmetrical dienes, so there's only one possible product. But there's two different, in each case, remember, like if we're talking about the rich getting richer here, in each case, the this carbon's got 2 protons, this carbon's got 2 protons. So, but the key point is that each one of these resonance stabilized carbocations are resonance stabilized. At no stage did I put the positive charge that wasn't resonance stabilized. So yeah, whenever we do these sort of questions, I always make sure that if either end has got the same number of protons on it, that it's symmetrical in some way, shape, or form. But if you can always, if one of the protons has got more protons on it, if one carbon's got more protons on it, that's the side you should attack. You're still using the rich get richer rule. But I just wanted to show you this, that there is like when a diene isn't symmetrical in some way, then you can get 2, 1, 2, here's another 1, 2. This is the 1, 4. So remember, 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. So that's where the 4. So you're counting from the carbon which attacked that proton. That's carbon 1. So if we did this reaction at low temperatures, we would expect the 2 major products to be these 2 here. And if we did this at higher temperatures, where it was under thermodynamic control, we would expect the 2 products to be these 2. So that's basically the, if you're adding HX to a conjugated system, that's the take-home message from that. Were there any questions on that? Okay, well, what we'll do then is let's see, was there a question? No. Okay, so what we'll do then is the second class of reactions with conjugated systems is what you guys did in the lab earlier this term, which was the Diels-Alder reaction. Now, this is probably one of the most famous reactions in organic chemistry. Diels and Alder won the Nobel Prize for it in like the 1950s. And it's a really interesting reaction in that you use a conjugated diene and you react it with another isolated double bond, or sometimes a conjugated system itself. And when the reaction works, you form a 6-membered ring which has got a double bond in it. So you're adding 1 + 1 = 1. So this is a addition reaction, and because you make a ring, they're sometimes called cycloadditions. Yeah, so this is and the other neat thing is that because they make 6-membered rings, and so many biologically important compounds have 6-membered rings in them, they've been used all throughout industry and pharmaceuticals, all sorts of places to do synthesis. So it's a super important reaction. So there's a whole bunch of really neat features to it, which we'll talk about, which makes it really cool. So the mechanism is largely believed to be is that it is a pericyclic reaction. cyclic. So this is that everything's taking place in a single step. So how this is commonly drawn is that 2 electrons go here to make a bond, 2 electrons go here to make a bond, and 2 electrons go here to make a bond. So we've formed this bond and this bond, and we've migrated that double bond over into the over here. So we break 2 pi bonds to make 2 sigma bonds. So remember, pi bonds, the orbitals are overlapping side by side, and in sigma bond, it's a head-to-head overlap. So sigma bonds are technically stronger bonds. So you're giving up some pi bonds to make some sigma bonds. Now, the 2 components of this reaction is the diene, which is what we got here, and the other component is what we call the dienophile. So this is the molecule that loves dienes. And the way that this works is most of the time these reactions are just carried out by heating them up. So you put them in some solvent that boils, high boiling solvent, heat them up, and the reaction goes. Sometimes people use pressure as well. And so there's, yeah, it's basically, it's like, remember with the Claisen condensation, all we did, or the Claisen rearrangement, all we did was heat it up. Same thing here, we just heat it up. So let's see here. We should talk about what makes a good diene and what makes a good dienophile. So the best dienophiles, we'll talk about the dienophiles first. The best ones have electron withdrawing substituents, functional groups, substituents. And when I mean electron withdrawing, I mean electron withdrawing from a resonance perspective. So like a ketone or an ester or even a nitrile group, for example. And so in each one of these examples, I can draw a resonance structure. We're going back to our friends, the resonance structures here, in which we move electrons onto electronegative atoms like this. I'll just draw the resonance structure down here. Black. Positive. So they all have got the same effect. Like they can withdraw electrons, like the nitro group can do the same thing. Aldehydes can do the same thing. So they all have got that similar sort of electron withdrawing substituents from a resonance perspective. So those are for the classic Diels-Alder reaction that was developed, these are the best dienophiles, things which have got electron withdrawing substituents. So that's important. So those are the best ones. Let's talk about, I'm going to erase some stuff over here. I'll erase this. the diene itself is a little bit less interesting, but I'll draw that in a second. So the diene, I'll draw it in. There's two different conformations that it can exist in, and so this is a rotation reaction, and they're given different. They're given different. They're given basically different names. And the important part has to do with the way that we're gonna do the, we're gonna make the bonds in this reaction. So this is the, what we call the S-cissoid conformation. And this is the S-transoid conformation. And so the reactive conformation is the cis conformation. So this one here is the reactive one. And the one here in blue is unreactive. Now, if we're talking about, if we look at these two molecules and we think about that, okay, so each one of these carbons is sp2 hybridized, so they're flat, right? So this molecule is trigonal planar at each carbon. One of them, the reactive conformation, we would think has got more steric sort of issues with it because those two carbons are getting close to one another. So the challenge for the diene itself is that the reactive conformation tends to be the least stable conformation. So sometimes this equilibrium might be facing the wrong direction. So this little arrow would be smaller in this direction. So the best dienes are the ones in which that cissoid conformation is locked in. So something like this. This is one of the best dienes ever because it can't undergo there is no rotation around this bond. So what we're doing here is we're rotating this bond to go between the two different conformations. But in this case, this one's locked in the reactive conformation. So it is permanently in the cis conformation. In other dienes, they will never get into the right conformation. Like for example, if we had something with a methyl group here and a methyl group here, the steric strain here, this is really, really bad. So this it would always be in the opposite conformation, which would be this. It would always be this one because this one's too high in energy. So with the dienes themselves, the best ones are when they're locked in that reactive conformation. And the obvious question is, well, why is this the reactive conformation and this one is unreactive? And we're going to get to that in a second. And the neat thing is that this reaction is controlled by the molecular orbitals of the two groups on them. So I guess we'll talk about that next. And then we'll talk about the fact that this reaction is stereospecific. So particularly in the case of the dienophiles, if that double bond has got some geometry to it, that geometry is conserved during the course of the reaction. Yes, you could do you could just do an entire course on the Diels-Alder reaction if you really wanted to. It's just, there's so much, it's been used so much, there's so much data on it, and there's some fascinating little tidbits locked in here. So it's just a super reaction. So I will save this little whiteboard here. And I'll talk about the transition state and how this actually works. And I'm going to draw the molecular orbitals of them. So let's clear all our diagrams. Okay, so we had, this was the reaction before. The very, just very basic. And so these electrons attack there, these electrons move there, these electrons move there. All is supposed to take place basically in one step, so it's a pericyclic reaction. But the way that this works is that the diene, and I'm going to draw the little orbitals. In the classic reaction, the diene uses its HOMO, highest occupied molecular orbitals. So in the last, when I drew the HOMO for a butadiene, there was a nodal plane right here. So one side, the shaded orbitals were on the top, and on the other side of the nodal plane, the shaded orbitals were on the bottom. And so it's the HOMO of the diene, and it's the LUMO of the dienophile. So with ethylene, remember we did this, the molecular orbitals of ethylene, you had two p orbitals, and the bonding orbitals, they were in phase. And the anti-bonding orbitals, they were out of phase because there was a nodal plane right here between them. So this would be the LUMO. So the LUMO of the group which is reacting, they have to be out of phase with one another. So I'll draw this in pink too. So this is the LUMO. And so when the two molecules are getting together and they're going to form their bonds, you will see that there is the appropriate orbital symmetry here, and there's the appropriate orbital symmetry here. And so this reaction is dictated by the orbital symmetry. Now, with regard to the cisoid versus transoid conformations, you'll notice that if I was to draw the trans version of this, let's get our pink color out. That was a nice one. And our nodal plane was right here. You'll notice that if we're trying to do this reaction with this conformation, that one of these orbitals might be close enough to, like this is close enough to react. But this one over here is way too far away, right? So it's too far, too far. So therefore, there's no reaction. So that's why only the cisoid conformation is the reactive conformation. So that's, yeah, this neat little orbital overlap. This is what's forming the bond. Okay, so that's basically the little molecular orbitals of the two components of this reaction. And if we were to build off, like, remember I said that the best dienophiles have electron withdrawing groups on them. Well, the interesting part is that if I was to draw, like, say, a carbonyl here, let's just make it a ketone. The LUMO of this ketone is still consistent with the LUMO of the basically just ethylene. This is the LUMO here. There's still two nodal planes, one's here and one's here, And you still have the two orbitals that would be reacting. They're reacting at the appropriate place. So, so when you have those electron withdrawing substituents, because they're part of the conjugated system of that, the double bond which is reacting, it's still a LUMO. So this would be there, that would be there, but the reaction's taking place, this part of it, that isolated. So it's still a LUMO. So that's just to be consistent there. Now the fun stuff. Okay, so that's basically how the orbitals overlap. Let's save this. Now the fun stuff about this Diels-Alder reaction is there's two really neat things. One is that it's stereospecific. So what in the world does that mean? So let's do that first. Oh, whoops, wrong screen. Okay. So the reaction stereospecific. So if we've got a so I'll do this with a ketone, and I'll do another reaction over here with a different one just to show you what I mean. So in this case, the dienophile is trans. And in this case, the dienophile is cis. So cis, remember, the two substituents are on the same side. Trans, the two substituents are on opposite sides. So when we do the reaction, the products, so we heat this up, heat. Let's draw our little arrows here. So form a bond there, electrons move there, form a bond here. Form a bond there, electrons move there, form a bond here. So we're going to be making our 6-membered rings. Draw them in brown. So that's the first part. Let's label our carbons here. Let's do this in blue. A, B, 1, 2, 3, 4. 1, 2, 3, 4. A, B. So, and now let's label our carbons again. 1, 2, 3, 4. A, B. 1, 2, 3, 4. A, B. So on carbon B, we've got a ketone, right? So let's draw our ketone. And let's choose a direction that it's going to be. Is it going to be up or is it going to be down? What do you want to see it? Let's draw it up because just for the sake of it. Okay, so we have to define that stereo center just for, okay, so it's up. Now, this is a trans diene. So that means that if this is up, then that methyl group has to be down. Of course, the enantiomer would also be formed, plus the enantiomer, which would be this. So if we drew this down, but this methyl group here would be up. But in both cases, the key point here is that these two groups, are trans. So it started trans and it ends trans. Now, conversely, with this other one over here, if this was up, then this methyl group would be up because it started cis and now it ends cis. The other enantiomer for this would be if we drew this down, this would also be down. But the key point is that it starts cis in both of these products. The two substituents are cis. So that's what we mean by stereospecific. So the geometry, the stereochemistry of the starting dienophile remains consistent after the reaction's done. So if it starts trans, it ends trans. If it starts cis, it ends cis. Let's do some examples then. Yes, let's do some examples. Let's do the example that you did in the lab. And let's do the example that just with a nitrile. Okay, so if I was ever doing this and I had to, I typically just label my, just so I keep track of things, I label my components. And that way, when I'm drawing the bonds between each component, I don't get lost. So in each case, we make a 6-membered ring. And so it's a cycloaddition, so a 6-membered ring. Plus, we've always got our double bond between carbon 2 and 3. So we need our double bond here. So on carbon B, we've got a nitrile. So I'm going to just draw it up because that's. So once I've declared that that is up, because our starting diene file was trans, so this is trans, that means that my product has to be trans. So if this is up, the trans product on carbon B would be down. So this would be methyl group, which is down, which is trans. Those two substituents are trans. So that's how that would work. In the second system, now we've got a ring structure for our dienophile is actually a ring itself, right? So this is, what did I do? So this is, we're going to have 2 rings. Again, let's label everything. 1, 2, 3, 4. This is A and this is B. Now you'll see that both B and A have got this anhydride attached to it. So now what we have to do is that there's still 2 protons on here, right? Proton and proton. If we want to make our drawing accurate, we have to declare, are the protons on A and B, are they both in the same direction or are they in opposite directions? Well, with this double bond, they're both on the same side. So we would draw, say, both of them up or both of them down. But the key point is that those 2 hydrogens are on the same side. So that means that the rest of the groups, the anhydride part, is on the same side. So this would be a cis ring junction because those 2 protons are on the same side. or the large ring itself is on the same side. So it's cis. So this starts out cis and it ends cis. Oh, I'll keep on going to the other screen. Don't know why my OneNote doesn't want to draw. Anyway, so that's the neat part about that. So it's stereospecific. So we need to draw the ring junction with the two protons on the same side. They both can be up or they both can be down, but they can't be one up, one down, because that would be trans. Does that make sense? Okay, good. Excellent. Okay, so now there's the last little bit to this. So there's one final part to this whole mess. So we're going to save this. I'm going to clear everything. So remember when I drew the transition state for this? And I discussed how, and this is for this reaction over here. Let's draw it for this. I'll draw it like this. I'm adding a couple little things to this. So I'm going to draw this ketone, which is the trans, basically the trans ketone here. And on my diene, I'm adding a little methyl group here, just for to show what's going to act, because it's kind of important. So there's actually two different transition states that we can draw for this ketone. We can draw one in which, I'll just color the orbitals here. We can draw this one, or there's another one. Let's draw this over here. This one's a little bit more crowded, but let's see if we can get it to look good. It's looking a bit too crowded there. Methyl group, and then this guy is, I'm going to just draw it way over here, exaggerating the length of that bond there. Let's draw the orbitals again. So this here, this here, this here, that there. So there's two different ways that we could draw this, and I've tried to draw it so you can see the overlap of the orbitals here. One in which the carbonyl is outside the diene, and one where the carbonyl, so this is the carbonyl, that electron withdrawing group which makes the reaction faster. And the other one, the carbonyl, is underneath the diene. And these two transition states give different products. But we only notice them if there's a substituent on the diene, like this methyl group I'm circling over here in the corner. So if I draw that methyl group on here somewhere, so the methyl group would be here. And we'll see in a second. So when the carbonyl is underneath, or the electron withdrawing group is underneath, this is what we call the endo transition state. And when the carbonyl is outside the diene, this is what we call the exo. Now, in the case of this trans system, the methyl group is in one instance, the methyl group's underneath, one instance, the methyl group's outside. But what determines if something's exo or endo is the carbonyl or that electron withdrawing substituent, which is sp2 hybridized. So ketones, esters, aldehydes, the nitro group or nitrile, whatever, that's the group. This group here dictates if it's exo or endo. So these two transition states give different products. And we'll basically be able to predict what they are. So I'm going to redraw them over here on the right, and hopefully it'll be a little bit more clear. So for the exo, if I draw the diene like this, I draw the dienophile, and I'll draw the dienophile in red, I guess. That would be the exo transition state. And the endo transition state would be, the diene just stays exactly the same, but the dienophile changes its orientation. So now it's, the carbonyl is underneath. So, and if you were to predict which one is the favored transition state, it's interesting. There are different times where each one is favored. But intuitively, most people would say, I think the endo looks probably more sterically crowded. It turns out it's the one which is typically favored. But there's a couple of factors which go into that. So I won't really, if we ever come across this on a test or something, I'll just ask you to draw the exo and predict the product of the exo, or draw the endo and predict the product of the endo. We won't really worry about which one is favored or not. But those are the two transition states. So the key point is that in the exo, the carbonyl is outside of the, it's almost like a step. If these are the orbitals that are making the bonds here, it's like a step down. Whereas the endo, this is the carbonyl part, it's like a sandwich on itself. So so the endo is sort of like a sandwich, and the exo is like a step. So those are the, but let's talk about the, well, we've got about 2 minutes left. But what we'll do at the start of next class is show how we can predict what the products are. And so the trans parts are going to stay the same because it's stereospecific reaction. The part which is different is the trans in relation to the methyl group, because that's where the two different diastereomers can form. But that's basically, so we'll just do a couple of examples of how to draw the exo and endo transition states and their products at the start of next class. And basically that's it for this little section. It isn't particularly long. But you would have noticed that this question was on the exam last term at this stage. So we just missed it by a course or class or two. So, all right. So yeah, I'll get to distributing out part marks and stuff for the exam pretty soon. I just got one thing to correct for my other class, and then I'll get to that. But it'll be done before Monday for sure. All right. And I'll get this posted online, and I'll find out why my OneNote doesn't work. But anyway, I hope everyone has a good day. And we'll see everybody next week. Unless there's a quiz. All right.